Hello dear students. So in this video we are going to discuss about the solution of one of the important question. So this question was asked in 2016, which is conducted by IISc here. Okay, so now let's see what is this question and what is this concept is, what is the base of this question, and from where, which concept, by using which concept exactly this question is to be solved, we have to see very clearly. Now let's discuss, and actually we have a separate concept for this. So okay, let us discuss about this. The value of this integral minus infinite to infinite sin x by x square plus 2x plus 2 into dx evaluated using the contour integration and the residue theorem. That means we have to use the Cauchy residue theorem, CRT को use करना है यहाँ पर. So CRT को use करके इसको निकालना है. Actually what happens, my dear students, so there are certain improper integrals, and by using there are certain improper integrals and definite integrals, we can solve it by direct methods, right? But when the direct method fails, so or directly we cannot integrate, or direct method fails, so then we have to take alternates here. So generally, for example, I will take it, I will give you certain examples, like a Dirichlet integral, that integral 0 to infinity sin ax by x dx is pi by 2, it is for a greater than 0, we say that. So that particular integral is directly we cannot do the integration process. So that can be derived from by using the Laplace transform or Fourier transforms here. So like that, there are certain integrals will be there, so which cannot be done by direct process, but instead we have to use some other methods to evaluate it, some other mathematical methods and evaluate it. So in that kind of question only here we have. So when the direct method is failing, that how you are evaluating such integral, so that you should know, and what are the things we have. And even he mentioned that using the Cauchy residue theorem. But to solve this integral here, Cauchy residue theorem does not help exactly here. Okay, so we need to know some more concept, this is a very special integral here. So to do this integral, so we should know that how by using Cauchy residue theorem we can solve it here. So for that, what is the concept is required? Let me talk about that. First, here I want to tell you about the point is the Jordan lemma. We say that here the Jordan lemma. See, actually this particular integrated can be evaluated by using Jordan lemma only. After application of Jordan lemma, so we can use the Cauchy residue theorem and evaluate it. But how exactly this process will go on? Let's see here. So I will not go into the detailed concept of the Jordan lemma here. Okay. Now, what is exactly a Jordan lemma here? So here I can say CR is a semicircle. Okay. The semicircle in the upper half of the plane. Okay, so that is, you see here, this is an integral you can take, right? So this is minus r to r, so this is the CR, generally we take it is here. Now this is the CR is the semicircular arc of radius r in the upper half of the plane, suppose. So if that is the case, limit r tends to infinity, as r tends to infinity, I want to say in a simple words that as r tends to infinity, the modulus of this integral along the CR, okay, integral along the CR, that means integral along the semicircle of a function that is e to the power of iz into f of z dz will be absolutely tends to 0. So this is the point which can help us to evaluate the given integral using CRT. Let's see that here. I am going to apply this Jordan lemma as it is into that integral. So how this is going to be used, let's discuss here. Yeah. Now we are considering, okay, now we are considering here, a closed contour. Now we are considering a closed contour which consists of the real axis along with the semicircular arc. real axis along with the semicircular arc in the upper half of the plane here. So now consider, now this is over here. Now we discuss like this. Consider C is the closed contour consist of real axis along with the semicircle CR, okay, along with the semicircle CR here. So therefore as closed contour C is a multiply connected contour, so therefore the integral C f of z dz is given by integral along this real axis from minus r to r f of z dz plus integral along the semicircle f of z dz d here. That will give you the closed integral C f of z dz here, as it is connected by two contours here. So the integral of C is given by integral along contour 1 plus integral along contour 2. So this will give you the integral of this function over the closed contour. Okay, dear students, so now this is the point here. Now the point is that here, here we are going to take f of z here. Now let us move on to the question here. Let us move on to the question. So in this question, if you observe, can we write this integral is equal to here the real part of e to the power of ix. Can we write like this or not? Sorry, it's not imaginary. Sorry, it's not real. It's a imaginary part, right? Imaginary part of e power ix, right? Imaginary part of e power ix divided by here x square plus 2x plus 2 into dx also we can understand. So this integral is from minus infinite to infinite. It's an imaginary part of e power ix by x square plus 2x plus 2. Now I am considering the f of x as here e to the power of ix by x square plus 2x plus 2. If this is our f of x for which we have to find out the integral here, so what is the f of z we can have here? F of z can be written as e power iz by z square plus 2z plus 2. Is it so? So now if I use these integrals into this integral, see that. Now here if I use this same function here e to the power of iz by z square plus 2z plus 2 dz is equal to here, yes, this is from minus r to r. There is one point you need to observe, my dear students. Here the point is along the real axis. So along the real axis that y is equal to 0. So therefore z becomes x. So therefore here it becomes f of x dx, and then here it is integral CR. So what is f of x? Okay, now I will write the f of x completely here. So the f of x I am writing it as e to the power of ix by x square plus 2x plus 2 into dx, and then integral along the CR. Now the point is f of z means e power iz into 1 by z square plus 2z plus 2 dz here. Z square plus 2z plus 2 dz here. Okay, so this is what the I have taken the f of z. Now the point is that we apply as r tends to infinite. As r tends to infinity, so this integral e power iz by z square plus 2z plus 2 dz is given by, it is equal to integral minus infinite to infinite e power ix by x square plus 2x plus 2 into dx, and then plus here. The point is that as r tends to infinity, according to Jordan lemma, please see this point. According to Jordan lemma, limit as r tends to infinity, modulus of this integral CR, that means integral along the semicircle in the upper half of the plane. So e power ia z into f of z dz is getting 0 or not. So therefore, so this goes to 0. So this becomes 0, my dear students, by using, so this integral becomes 0 by Jordan lemma. By using Jordan lemma, this integral will get 0 here. Once this integral is getting 0, now here we are clearly it is understood that, so this real integral is given by this complex integral, right or not, right? So the integral of this real function is given by, okay, so integral of this function is given by integral of this function. So therefore, to evaluate this integral, so we use this integral here, because it is in z, so we can, by applying the CRT, by Cauchy residue theorem, we can evaluate this integral value. We can integrate value. Once you get the integral value of this by using CRT, so we will get the value of this integral also here. So therefore, I can say here, coming to this point here, so I can say here, by Jordan lemma, we are saying that integral minus infinite to infinite e power ix by x square plus 2x plus 2 dx here, which is also equal to integral c, that it is e power iz by z square plus 2z plus 2 into dz here. Okay. So this integral is given by this integral. Now what I have applied is, so this can be evaluated by using CRT here, correct or not? So by using CRT means it is given by 2 pi I into sum of the residues, but we should know that at what are the poles which lies inside this semicircle here. What are the poles which lies inside the semicircle? What is the semicircle was here? This, sorry, inside this contour, I am sorry, inside this contour here. So minus r to r, so this is our contour which is the upper half of the plane. Now let's find out the poles here. The poles are given by what? The poles are given by here z square plus 2z plus 2 is equal to 0. If you solve this, z is equal to minus 2 plus or minus under root b square minus 4ac by 2a, okay, by 2a. So this will give you minus 1 plus or minus is under root minus 4. So it is plus iota. It's very clearly seen this बेटा. अभी यहाँ पर देखो एक minus 1 plus 1 है और दूसरा एक minus 1 minus 1 है. So x minus 1 and y minus 1 will be in which quadrant? X negative and y negative is in this. So this is minus 1 comma minus iota, and minus 1 comma plus iota is this. Okay. So therefore, so this point lies inside and this point lies outside here, and these poles are called simple poles here. So here the poles are getting simple poles and only one pole lie inside here. So therefore, what we do is that, so since z is equal to minus 1 plus iota lies inside C, and z is equal to minus 1 minus iota lies outside C here, So therefore, by CRT here integral C e power iz by z square plus 2z plus 2 dz is equal to 2 pi I into the residue at minus 1 plus iota. So this is equal to 2 pi I into, yes, my dear students, how to find out the residue of this function? See, the point is that it is a simple pole or not. So these poles are simple poles. So if I think everybody knows that if it is a simple pole, the residue at a simple pole is given by, or for the function like phi by xi, okay, for the function phi by xi kind of thing, so the residue is given by here phi of minus 1 plus I divided by psi dash of minus 1 plus I here. So this is the residue formula. So now if I take it here 2 pi I into, now I will take the 2 pi I into, what is phi of minus 1 plus I? What is phi is here? The phi is the numerator. So this will become here e to the power of I into z. Z means what? Minus 1 plus iota divided by the differentiation of the denominator. So what is the differentiation of the denominator is that 2z plus 2. So that means, so 2 into minus 1 plus I plus 2 here. So this is what the way we are getting the residue. Now this 2 gets cancels here. If you observe this 2 gets cancels, and this 2i is also gets cancels here. So then what is left here? So the what is the left point is that here pi, okay, and this is e power minus I, this is e power minus 1. So e power minus 1 and e power minus I, e power minus I here, the pi e power minus 1 e power minus I. So this is what exactly we are getting the integral value by using CRT, by using Cauchy residue theorem here. Okay. Now therefore I will use this value here. So let's see how can we write this value. So now therefore I can say integral minus infinite to infinite e power iota x. So what is e power iota x? Now you can write, my dear students. So e power iota x can be written as cos x plus iota sin x divided by, and this is x square plus 2x plus 2 into dx is equal to, and what about this here? So this value already I got it. So that is equal to pi e power minus 1 and e power minus I. But can I write, okay, let me write this e power minus I. But can I write this pi e power minus 1, and this can be written as cos 1 minus iota sin, okay, e power minus iota na. So it is cos 1, okay, cos 1 minus iota sin 1 we can write it. Iota sin 1 you can write it, because e power I theta can be written as cos theta plus iota sin theta. So this is what you are having. But actually हमको क्या चाहिए? What exactly हमको क्या चाहिए बेटा? हमको ये चाहिए कि इंटीग्रल sin x by ये चाहिए, cos x नहीं चाहिए. I want only sin x. अगर मुझे sin x by x square plus 2x plus 2 चाहिए, so what we have to do is that we have to equate the imaginary part on both sides here. Now we equate the imaginary part. Now I will write this integral as minus infinite to infinite cos x dx, okay, by x square plus 2x plus 2 plus iota integral minus infinite to infinite, so sin x by x square plus 2x plus 2 into dx is equal to here pi e power minus 1 cos 1 minus iota pi e power minus 1 sin 1, you get it. Okay. So now equate the real and imaginary part. Equate the real and imaginary parts. By equating the real and imaginary parts, so what you are getting here it is, we are getting that integral minus infinite to infinite cos x by x square plus 2x plus 2 dx is equal to, here it is pi e power minus 1 into cos 1, okay, and integral minus infinite to infinite sin x by x square plus 2x plus 2 dx is equal to, here minus pi e power minus 1 into sin 1. So this is the answer for this question here. So this problem is, यहाँ पर क्या है ना बेटा, ये इंटीग्रल ये डायरेक्ट CRT से नहीं आएगा. आप यहाँ पर जॉर्डन लेम्मा का कॉन्सेप्ट अप्लाई करना, तभी ये इंटीग्रल आएगा. Okay, so this is an exclusive question. Okay, but later on side this part is removed from the syllabus, but here if at all this comes from the examination, so you can learn it. Okay, right. So now the answer for this question is, that is minus pi by e sin 1 here. So this is the answer for this question. Option A is the right answer for this question. So there's a lot of concept behind this question. So if anybody is interested, so they can look into this and understand, and then you can do the remaining questions of sine, cos. When the denominator is changed, the denominator may change, that's it. So he may ask for cos sine here. If he asks for cos, you go for equating the real part, and if he asks for sine, you go for equating the imaginary part here. But only then, if any question comes from this side, only when the denominator will change, that's it. Only the denominator will change. So if the denominator function changes, so only the poles will be changed. If you can find out the poles of that and multiply by 2 pi I and find the residues, and 2 pi into residues will give you that integral value. So directly we can equate with the real and imaginary parts and get the answer for this. So this is the very an interesting question. Okay, right. Thank you.